Hello and welcome to the show. My name is Relvit. This is Do All the Things. On today's episode, more PWM switch mode tomfoolery. For I am going to be modifying this old flashlight with LED and a dimmable PWM power supply. Stay tuned. If you've been following the company, you might be aware of my fascination with switch mode power supplies and the general tinkery that I put into them. In a previous episode, I built this very simple 6-volt power supply to run this power bulb, and I mounted it on my bike. But at some point, I removed that from my bike because I acquired some proper LED bulbs. There were 3 of them, 2 different kinds, a couple warm white low output ones that were ultimately useless for the bike, so I didn't use them. But then I got this nice neutral white, higher output one. I put that on there in an H3 automotive fixture and it works well. Very happy with it. Got, way more brightness out of it and like 2 or 3 times the runtime because it uses less power. So what did I do with the other H3 bulbs? Specifically these little guys. They are useless for an application like a headlight, but I found them useful in flashlights. Specifically this one. This is some unit that I probably got from a Value Village for who knows how much. I don't know where I got it. It's got no name on it. I just, made in Hong Kong. I just got a kick out of it. The black and the red, that classic 6-volt flashlight. You might not be aware of this, but I used to collect flashlights. I got a box full of them. Some of my nicer ones are on display, and I've certainly modified on them, hot-wired if you will, trying to get more power out of them. At one point in human history, there's a place called Candle Power Forums. You could get any aftermarket upgrade you needed for a Maglite. You remember, once upon a time, those hardware store specials, the big 1 million candle power rechargeable lights that are just absolute garbage. They worked great at first, but they didn't run very long, and they used lead acid batteries. So if you ran down this light to the point that you actually saw, oh, the battery's dead, you've damaged the battery. And if you didn't charge it right away, you damaged the battery. So you probably only got a couple uses out of it before it was garbage. So it just so happens you could find scrap parts for it. And this H3 reflector, which is one of the cool things about them, they used H3 bulbs, came out of one of those 1 million candle power batteries. And wouldn't you know it, just to my luck, it fit perfectly into this flashlight body. So what did I do? Well, I modified it with a switch. And then I grabbed one of those lead acid batteries and I turned it into one of those 1 million candle power spotlights. And it was fun for about 5 minutes because the battery would run down really quickly. So this thing's been sitting in a junk bin forever. Not sure what I was ever going to do with it until I got these bulbs. See, these bulbs, well, they only consume about 350 milliamps. So a battery runs a long time. So I did it. I threw this in here with this old battery and I've been using it ever since. It has the magical ability, like, you just sit it like that. You just sit it like that on a table. And then it just beams against your ceiling. And if you have white ceilings like I do, it fills the room with nice mood lighting. I've actually been using this thing as a lamp on my end table beside my bed. Every night while I'm chilling in bed watching a couple of YouTube flicks before I crash out, I've been using this as my lamp. Especially with this bulb, it doesn't have a spot pattern. It has this weird X-shaped flood patterning. You'll see it later, but that actually makes it kind of like it's actually a really nice flashlight to use now in this configuration. So I decided I want to permanize this, officiate this, and use my PWM knowledge to build a custom power supply for this. I decided to solve a problem, and that problem is all these packages of batteries that I have. Alkaline AA's. These are actually medical waste. Medical devices that use batteries are changed out on a schedule regardless of whether the battery is depleted or not. And in many cases, that battery still has plenty of life left. Now I have a stockpile of them. I can't use them fast enough. These batteries are over 10 years old now, and I've gotten to the point where it's either use them or lose them. To solve that problem, I'm not only going to create a power supply for this thing, but I'm going to create a battery drainer. So what I've done is I've acquired an 8AA cell holder with, your 9-volt pickup so I could quickly and easily attach it and detach it from the circuit. With this, I'm going to be able to use up these batteries. Because you see, alkalines, they have a problem. If you compare the voltage to the capacity runtime, you could have a strong battery, but then as you operate an alkaline, the battery voltage drops like this. And here's its usable capacity here, right? This was especially notorious in Walkmans in the 90s. They needed a minimum voltage to operate, but it still holds true today. You end up hitting a cutoff point where the device can maybe no longer operate off these batteries, but they still have half of their usable capacity. I say that alkaline batteries have a half-life in that way. It's like they're not strong enough to run your devices anymore, but they still have a bunch of capacity left in them. So how do we squeeze out that capacity? Well, by using 8 of them. This is a 6-volt bulb, and in testing, I can run this bulb nicely off just 4 cells. But of course, when the cells hit the half-life, your flashlight goes dim. So by using 8 of them, well, each individual cell is going to get run down to a very low voltage before I don't have enough voltage to run the bulb anymore. And to regulate it down, we're going to use a PWM circuit. So this breadboard tomfoolery is what I threw together to do this. We got ourselves a bulb, we got ourselves a battery pick, and then we have this potentiometer I've had in inventory for over a decade that I never had a use for until now. 50K with a switch, which is perfect. Give it a little flick, and oh, yeah, bud. Dimming. A dimming switch mode. I actually went with dimming. I wasn't initially going to use dimming. I was just going to be like, okay, whatever voltage in, regulate it to 6 volts out. But I had the problem where at the time, I didn't have the ability to devise a circuit that would automatically adjust your duty cycle. You could just run against the rev limiter and let that regulate and run a really high duty cycle, but it's going to whine because the rev limiter can't switch as fast as the circuit itself. So it ends up, you get a little out of the inductor, and oh, I think I can example it here. I did that with this guy. You hear that? That's because this circuit's more basic. It just runs against the rev limiter. So what do I mean by that? Well, let's take a look at the schematic. We have the little dimmer component here, and we have our batteries, and it comes in, it switches it on, powers the main rail here. There is our Toshiba TC4 S584 Schmidt trigger inverter in a relaxed oscillator configuration, my favorite for generating a PWM. Of course, with its 0.1U bypass decoupling, I forget what it's called, capacitor. We start off by regulating with this 1K resistor and 5.1 volt Zener diode the input of this TC4. Even though the TC4 can handle higher voltages, we still regulate it because it gives us a consistent high-low voltage threshold and hysteresis so that we get a fixed frequency. Otherwise, the frequency would change with the battery voltage. And then, of course, to generate our duty cycle, two SD103 Schottky diodes go to either side of that potentiometer. The center of the potentiometer returns to the input of the inverter with a 220p capacitor. So as you know, with a relaxed oscillator, we create a feedback loop. An inverter, whatever you put into it, you get the opposite out. So if we put positive in, we're going to get negative out, negative in, positive out. So if we create a feedback loop, it keeps switching itself. Positive out to positive in, switches to negative out to negative in, switches to positive out, and so on and so on. And this process is slowed by the capacitor that has to slowly charge and discharge. And the speed at which the capacitor charges the discharge ends up ultimately determining our frequency because it slows down the time it takes to hit those voltage thresholds. And that's how we generate our pure square wave. That goes through this 10K resistor into an MCP 1406 MOSFET driver. In order to operate a MOSFET correctly, we need to hit that gate with a good jolt of voltage. The small signal coming directly out of the inverter is often not enough. It is in some designs. I did design a 5 volt to 12 volt boost system in which I'm driving the MOSFET directly. That's because the system's running at 5 volts, so certain dynamics change there. Of course, we need bypass capacitance on this guy. I'm using a 1U. I usually use a 4.7 to 10. I might up that value. MOSFET drivers get angry if they don't have that capacitance. Trust me. And then that drives the MOSFET. We've got some input capacitance directly on the MOSFET so they can get all the power it needs when it switches on and off without disrupting the rest of the system. And then from there, when the MOSFET switches on, power flows through the inductor and out to the load. The inductor builds a magnetic field. When the MOSFET switches off, the magnetic field in the inductor discharge is filling in that gap when the MOSFET's turned off, at which point this side of the inductor is going to go negative because it's trying to power the circuit after all. This SB160 Schottky diode, which, as you know, a diode is a one-way valve, is going to fly open and let that negative get to the ground rail. Then we have our output capacitance to smooth everything out, and then that powers the load. These 220U capacitors, they're arbitrary. They're probably a bit bigger than I need for this circuit. There is math to figure out the capacitance values, and I have done it before. But at this point, I just use my instinct. Capacitors are like reverse Price is Right rules. You need enough capacitance without going under. If you go over by a margin, it's going to be okay. Unless you go grossly way over, you can actually put too much of a load on the circuit. But you'd have to get a big damn capacitor before that's a problem. So what did I mean by the Rev Limiter? Well, that's this pupper over here. That's half of an LVT 817 optocoupler. On this side of it is an LED. We have a 1K resistor to roughly bias this LED. I usually shoot for about 10 milliamps current at my voltage, but you can slightly fine tune this. Ideally, I would need less, but I loosened up that a bit so that I could raise the voltage just here. And then that goes on its negative to a 5.1 volt Zener diode. As you know, a Zener diode is like a pressure relief valve. It's a valve that's going to kick open when it hits a certain amount of voltage pressure, in this case 5.1 volts. We take that 5.1 volts, add it to roughly the 1.2 volt drop we get across this LED, and we get about 6.3 volts. So when we hit our threshold of about 6.3 volts here, there's enough voltage pressure to force open this valve, which lights up this LED. What that does is on the other side of the LTV, it fires this light activated transistor, which grounds out the signal going to the MOSFET driver, essentially turning off the MOSFET. So if our voltage goes too high, it shuts off the MOSFET. The voltage drops a bit, it turns back on, and the cycle repeats itself. And that's what I mean by the Rev Limiter. This circuit is oscillating at about, I think, 120, 130,000, 120 or 130 kilohertz. But when this thing kicks on, it can't oscillate, it can't switch fast enough, it can't react fast enough. So what ends up happening is instead of 120 kilohertz, it goes down to about 12 kilohertz, and you start hearing it whine, which is what's happening on here. The duty cycle on this particular unit is set up so that when the battery kind of depletes to a sweet spot, it's the correct duty cycle to run 6 volts. But when the batteries are really full and slightly higher voltage, they're hitting up against the Rev Limiter, and the Rev Limiter is what's stopping the voltage from getting any higher. It's what's doing the regulating, and then you end up with the squealing. Now, I don't want that squealing in the bedroom. Well, not that kind of squealing anyway. So I decided to use a dimmer just so I can variably adjust the duty cycle. Turn it up till you hear the squeal, and then bring it back down a tenth of a turn. And then boom, it works. As the battery depletes, I can turn it a bit up to compensate. If I run a stronger power supply, a bigger, higher voltage battery, I kind of spec'd out the circuit so I can do that. I can just turn it down a bit, right? So that was just my cheap hack solution to not have to have that squeal, and consequently, you end up with the convenience of dimming, which in practice, because I have been using this like this for a couple days, is actually a useful feature that I'm gonna like. So you might notice in here I have this 4.7K resistor. That is a new addendum I'm adding to my voltage feedback Rev Limiters. It bleeds a little bit of power through here to bypass this guy, which actually raises the voltage threshold a bit. So this thing, I believe, is regulating now to about 6.5 volts. I wanted a little bit more. Oh, no, we're still 6.3 volts. So then remind me again what voltage we were getting without that 4.7K. Yeah, 5.9. Okay, that's what I was compensating for, just to get a little bit more out of it. So yeah, with this resistor and this resistor, you can fine tune on the threshold of the Zener. But what's this 1K resistor here? Well, let me explain, because there's a whole nother section to the circuit that I kind of obscured from view up until now. An AS, aka LM393 voltage comparator. It's an op-amp that has an open collector output. Whereas normally op-amps could have either high or low, much like other logic circuits. It could put positive and or negative output to here at a very low current potential. The AS939 just has a transistor that will ground this out. So this output is either high impedance, there's either nothing there, or it grounds it out, and that transistor has more current potential than a typical op-amp, which is fine for this application. Basically, this is my under voltage protection circuit. So if my batteries run down too low, it has a way of telling me. Now, I don't care about this with the alkalines. I want to suck every last watt out of these guys. But where I do care about this is with rechargeables. At some point, I'm going to use these up, and I'm not just going to chuck out the flashlight. No, I'm gonna put a different battery system into there. As an example, while I've been prototyping this, I've been using rechargeable AA's. I actually have an 8-pack of these Evereadys, which are also getting long in the tooth, so these two I have to use or lose. But when I'm done my alkalines, I can switch over to rechargeables. And like every rechargeable, even though they're less susceptible to it, these will get damaged if we over discharge them. We will damage their lifespan. Now, you don't hear about this much because most devices we run off rechargeable batteries of this nature will stop working when they get too low. But this circuit has the ability to sap every last watt out of these, and I don't want to damage them. So we have under voltage protection. Also, at some point, I might want to use 18650 lithium ions. I've kind of designed this circuit so that it could be more modular. I can adjust it to other power supplies. For the most part, this guy can handle up to 18 volts of input. I think that's the maximum rating of the MPC and the TC4. So up to 18 volts is what we got. All I need to do is adjust it for the battery. And right there, we have a little adjustable potentiometer. So what happens with this guy is we have voltage reference on the inverted input, in which I'm just stealing a bit of signal from the 5-volt junction on the TC4. I should probably have some sort of resistor there, but it didn't seem to be necessary. Just feed a little bit of that 5 volts in there so it has a common reference. And then we have our battery voltage being fed via a voltage divider to the non-inverted input. If the voltage of the plus input is higher than the negative input, the output goes high, or in the case of the AS939, nothing is there. But if the voltage on the plus goes under the voltage of the minus, then it grounds out this output here. So basically this voltage divider, we dial it in so that it puts 5 volts here at our target voltage. This 22K feedback resistor accelerates the process. Otherwise, it would slowly transition to on and off as we hit that threshold. When this grounds out, or starts to ground out, it will send a little bit of that signal to the input to accelerate it, and we get a harder, more jagged response. So instead of like if you hooked an LED to the output, you would notice it start to dim up. Instead of just turn on, it would start to dim up. This feedback, which I found 22K was the sweet spot for this application, the LED would just kick on. So what happens when this goes to ground? It sends the signal over to that 1K resistor we saw, which grounds out this junction here, bypassing the Zener diode. What that does is it causes our voltage feedback rev limiter to react to that instead of the voltage feedback, and it actually pulls down our output. So with the 1K resistor, we kind of need that to decouple it from this circuit to begin with. Otherwise, this stuff will interfere with how this works. But the 1K resistor, along with the 1K resistor here, means this thing isn't going to completely turn on. Indeed, this circuit, if it kicked on without that resistor, would just shut the light right off. It would just shut off the MOSFET. But in this case, it's going to run that slightly dim, and it's going to start to influence this. That's actually going to pull down the voltage, and I get something like 2 volts of output. Bulb is full power. Oh, I'm getting 6.4 now. I must have poked something. And then I hit voltage cutoff. Boom. It drops down to 2.75 volts and the light gets really dim. So with that 1K resistor, we can kind of fine tune our light output. And then we'll see that when we go to turn it on, no matter how we adjust it, that's basically going to tell us that our batteries are depleted. And well, in theory, we won't be completely without light. So, you know, you kind of, if a flashlight's gonna crap out on you, you kind of want a bit of light. I'm not really worried about being left in the dark with this thing because I'm just using it as a table lamp. Ideally, I think I might want to lower that value a bit so that you can still get some light output, just enough to get you out of the situation you're in, kind of thing. You know what I mean? So that's the circuit. Dish is the layout. Oh yeah, it got fun. I'm getting better at these little circuit designs. The target size was a 4x6 cm perf board. And oh yeah, it's hard to follow. We got battery in here, out to the switch returns here. That powers this main rail. Here's the 1K going to the 5-volt one that supplies power to the TC4. That continues on up to the MOSFET where we have our main filtering. Ideally, we should have some sort of bypass capacitor on the input, but with battery power, I'm not too worried about it. It further goes down, powers the MOSFET driver, powers the op amp. Coming off the TC4, we have our little bypass capacitor. That goes through voltage reference to the inverted input of this side of the op amp. Also connected to our TC4, we have center and then our low setting and our high setting on this multi-pin connector going to the potentiometer. Our 2 diodes, they come off the output, connect together here, go out, come back, go on to the input. There's our 220p to ground because this is our ground bus we have going down around here. And then our output feeds to that 10K, feeds past the 817 into the MOSFET driver. Out of the MOSFET driver, the 2 sides have to get connected together because they have separate high-low outputs. That drives the MOSFET. MOSFET output to 330U microhenry inductor, then our output capacitance, then our output. Meanwhile, that output goes to the 1K, goes to the input of the 817, 4.7 leak, 5.1 Zener, and then here's our 1K to be pulled down by the output of the op amp. 22K feedback goes to here. Here's our potentiometer on the board. There's a capacitor I forgot to mention. It's just another 0.1U that kind of buffers this voltage divider into there. Now the 393 is a dual op amp. We only need one side, and as a cheat for space, I'm letting everything on this side get grounded out. Again, this is just open collector to ground, so we can confuse these inputs all we want. All it's gonna do, it's gonna take ground here and connect it to ground there. Like, doesn't really frickin' matter, bud. My plan, if I don't want voltage protection, is to just pull the 393 out of the socket. So I think that's the gist of the circuit. I got this multi-pin connector here. This is actually for balance charging, but it's gonna be perfect. 5 conductors for that potentiometer. So now, I suppose I have to build on this. It's time for a perf sesh. Well, that was certainly an adventure. I made a mistake. I forgot to add the catch diode, and the schematic is this guy right here. Very important because it lets the negative go to ground. If you don't have that, this MOSFET gets real hot as that power just slams into it. So now it's just kind of sloppily stuck over there. But for the most part, I think it's done. Unless I did something wrong here, which, you know, I got to turn it on to figure that out. It should work. So I need to just make leads for the bulb. So that's going to go onto the bulb. This thing, I think I want to do a nice wrap. That's the negative line. We'll wrap it up to about this point here, in which case it will converge off, go up here, and it has to go onto about here. So right about here. And then give it a strip. And then supposedly these red conductors are good for 22 gauge wire, so we will stick that in there and see how well that works. I guess so. That's a bit of a weak spot there. Half because, you know, we have some exposed positive. We might want to do something about that. Chances are we install this and we leave it installed, so maybe a little bit of tape will do. Now, we could put power to this, but it's not going to do anything until we hook something up to that. We need to get the potentiometer going. Where is it? Where's my pot? Who took my pot? Ah, there it is. So we're going to solder leads onto the pot, take these test leads off. I'm going to leave that red one on briefly because that represents high. Or you know what? We'll mark it. The idea is that is where it points when we turn it all the way up. So we want that to be full PWM frequency. So our multi-pin connector lead here goes into the bud like this. I've already made it so that red is the battery positive input. We're going to want a little bit more slack. I want to proper wrap these around, right? I don't just want to stick them through a hole and freaking call it good. Wow, these are crappy little wires. Black's our battery return, or switch return. Get that on the other switch side. Center is yellow. That means it goes on the center lug. Green is our high, which should be, because we turn it towards this pin, high will be the opposing diode, and then this is low, turning it down. All right, this circuit is now a thing that exists. So let us do one of these. It's disconnected, there shouldn't be a short circuit. Let's turn it on just a little bit here and do one of these. Oh, you know why? I forgot to put in the crystals. We shouldn't need the voltage cutoff, but we definitely need the MOSFET driver. Oh boy. Oh, we got bright. Turn it down. Oh, well that's wonderful. We haven't got any dimming. Dimming don't work. Dimming don't work. Does that mean our TC4 does not oscillate, sir? All right, this is the troubleshooting portion, because there's so much you can get wrong when you're doing stuff this way. Okay, so let us hook up the meter and test our output voltage, see if it's even regulating. It is not, it's giving full power out, in theory. Battery voltage is 9, output voltage is 8.6. Our Zener's good here, good here. Thought I smelled something strange. Oh, let's fire up the electrovision, bud. So if you look here at the electrovision, if I probe on the top of the TC4, you're gonna see it's indeed oscillating, but with a very high duty cycle. Now is that signal making it to the input of the MOSFET driver? I do not see signal in the MOSFET driver. I do not see signal in the MOSFET. Is it making it to the other side of this 10K? Yes. Is it making it to this side of the 10K? No. Let us see if our duty cycle responds to our pot turn. It does. Okay, so the TC4, the oscillator's fine. Oh, I forgot to make this connection here. Oh, derp, mistake number 2. Obviously, there's more things that I've forgotten here. Even though the signal oh, what? Oh, I also accidentally ran that to there. You derp. Okay, so I made 2 little mistakes. This line was supposed to go to there. So basically, I had high parked on the signal bus. Man, I don't get how I can derp so badly sometimes. The other mistake is I forgot to connect this connection here. LVT to ground. That's 3 mistakes now. 3rd time's the charm. Fortunately, that 10K resistor was in place, so it didn't backfeed power to the oscillator. That might have been bad. So now let's try it. Ha! And there we go. Turn on. It feels like it hits the high voltage threshold a bit earlier. That might be because I have less losses, because this thing's not, it's not on a breadboard. You get losses on the breadboard, right? So let's check our output voltage. 6.5. Yeah. And I hear the whine. Bring it just down under, no whine. And then it just goes down from there. Oh, it looks like it's working perfectly now. All the way down to 2.4 volts. Let us check our reverse voltage. Oh, look at that, kicked right on. Or not reverse voltage, our under voltage protection. So when I'm ready, I need to recalibrate that for 8 volts. I need to get a variable power supply to do that. But in the meantime, I'm not interested in under voltage because I'm gonna be using alkalines. We're just gonna choke them right out, bud. Now it's a question of getting it installed. All right, I got Snotty Dread warmed up here. We're gonna wanna do a little bit of this action. Make these wires not break off on us and keep these caps still. So, I need to install it into this thing here. In order to do that, see that hole, the pot isn't gonna go through that. So I've taken this piece of scrap aluminum and kind of round shaped it there. I need to drill a hole through it to mount the pot, pretty much right center, which is gonna be hard to determine from this angle. Scrap aluminum. Really? All the way over there? Yeah? Okay. I was banging on it with a hammer to kind of get it that shape to kind of fit in there. This actually came out of a Leanne Lee case. Let's get her on the edge here. Let's punch that hole. Now I gotta drill that hole out big enough for the potentiometer. How big's the hole in the potentiometer? Looks like a 1/4 inch. Yeah, 1/4 inch should do. All right, let's punch it. Remember, if you want to impress her, chamfer and deburr. So I'm assuming it fits in like this. No, it doesn't. It fits in the other way around. Okay, so potentiometer is going to be oriented generally this way. Uh-oh. A hole's a bit so small, so this is a little bit bigger, 1/4 inch. Oh. We're just gonna put our tool through here and ream it out a bit. Oh, look, we can kind of thread it in there. That's nice. It'll lock it into place. Well, hold up here. You gotta go far in that, bud. Yeah, boy. Okay, carefully now, without damaging our threads. There. Does this sit in here nice, sir? Yes, sir, I do believe it sits in here nice. Will the reflector clear? Yes, it'll well clear. The only problem that we have is these wires are gonna break off of there right easy. I guarantee that. Maybe, just maybe, we can goop it. Glue guns, is there nothing it can't do? Oh, there's lots it can't do, bud, trust me. We want to stick it to this plastic here now. Let's just good old-fashioned rough it up. Do a bit of surface prep. Huh, where's my booze? There's my booze. All right, so this is gonna be a careful operation here. Just gotta kind of make this all nice and accurate. So the center's nice, you know. I just don't want it to look all derpy. Not the rest of this is derpy. It's just derpy. Derp, 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 derp. Well, you know what? Before we glue that down, let's get the nut on. Oh no, 10's perfect. Now it's not gonna move on us. Oh, you know what? That nut fits in that hole so well, we can't possibly seat it uncentered. So let us, and tomato, stick a goop on one side, a goop on the other side, and seat it down in there. Then we're gonna draw goops over top of it. Oh, this idea is a bit weird because I expected maybe I was gonna be able to get this iron in there better, but apparently not. So we're just pumping a bunch of goop down this hole and hoping for the best. Got a toothpick handy, we'll kind of spread it in there. Fortunately, it's not gonna be a lot of push force. That should be good. Now, what are we gonna do with this thing? I just kind of planned on tucking it into some foam with the batteries on the other side. So let's get the reflector on. Spin that up. Let's get some tape on that connection. Canadian Handyman secret weapon, hockey tape. I think I'm also gonna put some on the back side of this just to cover those connections. Not quite epoxy potting, bud. Oh, forgot I wanted to glue down the pot. No walkie potty. Boom. Look at that nice little package. Way nicer than what was in there before. Way nicer. Let us get our battery bank. Let's get these out of there. Let's get these in there. Pile alkaline. All right, so how I did this before is I just had this stuffed with foam. So I'm going to take our driver board, connect it, jam it in there, put this block of foam on there, get our battery, jam it on the other side of the foam, and then jam more foam, and then that should work now. The lens needs a cleaning too. We got like condensation inside. Oh, I think it got steamy. I think something was starting to get too hot there. Don't clean the reflector. You'll never get it good again. Funny thing is this thing was somewhat waterproof before. I don't think any of the components in there under this load are gonna get hot enough to compromise that foam or need so much cooling that they can't be jammed with that foam. Might wanna reinforce on that a bit. Okay, can we finally put this together now? Finishing touch. Will this fit? Oh yeah, bud. I have this one-off knob. I think I found it at a venue I was working at, and I haven't actually had a practical use for it until now. Oh boy, look at that. It fits perfect, just enough length. A little slanted, but actually, oh, it is rubbing up against the front. So my pot's not sitting perfect. That rub-a-dub-dub action is just a little bit of burr action right here. If we could just shave that down. No, we need to seat it just a touch proud. Okay, that's fine. Oh, that feels nice. I think it's gonna be good now. New life to an old flashlight using logic, as in PWM, as in, yeah, you're not good at this, are you, bud? You can build stuff, but your talking's all weird. Yeah, you're right, bud. Just enjoy the show, which I hope you did. If you did, stay tuned, because I like doing this sometimes. In the meantime, we're gonna end this off by showing you this thing's general polar pattern, because I beamed this against the ceiling. How's that look? Yeah, see that weird cross shape, that weird X? That's the light pattern on this thing. So it nicely bounces off the ceiling without a harsh spot and makes for really nice mood lighting. And now it's officiated, and now I could use up all these double A's, and I can control it with one finger. I've lost its water solubility now. Actually, no, it is water soluble now. It used to be waterproof, but now we have a place to leak in, so I'm not gonna use it under wet conditions. But in the meantime, I think we're done here. Hope you enjoyed this. If you did, stay tuned. I already said that, bud. You already said that, bud. Okay. It's time to eat. Yeah. Oh boy. Oh, yeah. There's your horror story right there, bud.